Our final application of rationalizability from Chapter 8 is the Becker crime model. In this model, we have two players. We have a government, who we denote G, and a criminal element. Think of it as a criminal syndicate as a player, which we label C. Okay? G, the government, chooses law enforcement level of effort X. So X, you could think of X as a number of police officers or something of that nature. It's the resources spent on enforcement. And C, the criminal element, chooses crime level Y. How many houses to rob, how much money to launder, things of that nature. Okay? These are simultaneous and independent choices made by these entities. So they have to form a belief about what the other one's going to do and then decide how much effort to put into this game. We're going to assume the utility of government is equal to negative x times k to the fourth minus y squared over x. Okay? Here, k to the fourth power is the unit cost of enforcement. So it's like in police officer interpretation, if x is the number of officers, k to the fourth is how much each officer costs. Right? Why k to the fourth? Why not just k? Well, it makes the math work out really nice and cleanly. So the fact that it's k to the fourth rather than just k is a convenience mathematically as far as the solution is concerned. Although it makes the setup look a little more complicated, everything falls out more nicely that way. Negative y squared divided by x. We can think of that as the societal cost of crime. So we see that the more crime there is, as y gets bigger, the society is more negatively impacted because it's minus the societal cost of crime. We also see that the cost of crime is increasing exponentially in the amount of crime. So the more crime there is, it impacts society negatively at an increasing rate, right? But it's mitigated by enforcement effort. So for a given value of y, the more x there is, the lower the negative societal impact of crime. Having officers in the street maybe eliminates the collateral damage of some crime. Okay? So this is the utility function of government and the utility function of the criminal elements. We're going to assume to be y to the 1/2, same as just y squared, right? Divided by 1 over divided by 1 plus x times y. Okay, and here we say y to the 1/2 is the value of crime. All right. So this is a very standard assumption economic. We're here assuming concave utility, right? So more crime means more value coming in from crime, but the value is increasing at a decreasing rate. The last couple of models we looked at, we assume linear utility for simplicity. This is a more standard assumption in economics, where we assume that we like more resources, but our love for them is increasing at a decreasing rate. Each additional dollar that you get back from crime is worth less than the previous dollar. Okay, and then we can interpret 1 over 1 plus x times y as the probability of evading capture. So note that if you don't commit any crime at all, if y is 0, then the probability of evading capture is equal to 1. So we're assuming that there is no false arrest here, so that the only way arrested is if you are committing crime. And then for a given, regardless of what the level of crime is, if the level of enforcement is 0, if x equals 0, you still are definitely going to get away with it, so you have no chance of getting caught if no effort is put into law enforcement. The bigger that x is, the bigger that y is. the bigger the denominator of that expression is, which is then going to make the probability get smaller, so it's less and less likely that you evade capture, the more crime there is and the more enforcement level there is. Okay? So next, I'm going to give you, rather than derive, the fact that UG and UC are both concave in their individual choice variables. All right? This model is complicated mathematically. The level of complication is more than what I expect for you to be able to solve on your exams. I'm not going to ask you to use the product or chain rules, which we're going to have to use on the utility function for criminals. So I'm not going to, the math goes beyond what I'm expecting in the class, so I'm not going to bother dealing with the second derivative, so I'm going to just take as given that it's concave. I still think there's value in understanding this model, so if some of this derivation of the best response functions gets a little tough for you, just kind of stick it out, take as given what the best response functions are, and then we'll think about rationalizability for you from that point, okay? All right, here we go. Let's just rewrite that utility function of government so that I can take the derivative. The utility function for government, again, was equal to minus x times k to the fourth power minus y squared divided by x. So the government's going to form a belief about what y is, what the criminal level of effort is, and then that makes this a one variable choice problem because k is just a parameter of the model. They know what it is, it's given. Okay, so the derivative of this utility function with respect to x is equal to negative k to the fourth. Because again, k is just a constant, so negative k to the fourth is just some number times x. So the derivative is just that number. The second one is going to be minus, well, what do we have? We have y squared times x to the minus 1. So it's minus, so the minus goes out in front, minus y squared times x to the minus 2. Right? We could have also used the quotient rule if we'd like, but I just decided to make the divided by x just the same thing as x, times x to the negative first power. Okay? Put a negative 1 out in front times y squared. Why does y squared? Nothing happened to it. It's just a constant. Again, we make a guess about what y is. That's y, so in fact, we can make that a y bar. So we make that a guess about what y is. Note that's not y to the negative 2. That's y bar to the second power. And so we had a negative 1 exponent on x. We put it out in front. So minus negative 1 y squared times x to the minus 2 because we had to subtract the 1 from the exponent. Okay? Next, we're going to set that number equal to 0. Well, yeah. We'll set that equal to 0 because I've given you that this is a concave function. So it'll be solved at its maximum when it equals to 0. So plus y bar squared times x to the minus 2. Okay? And of course, we can swing the k over to the other side. Oh, yeah, sorry. I should have gone a little bit fast there. It equals 0. And since that equals 0, I can throw the k to the other side. So y bar squared. X to the minus 2 is the same as 1 over x squared. So it's x squared here is simply equal to k to the fourth. Okay? So from here, we have y bar divided by x, the whole thing squared, equals k to the fourth power. I can then take the square root of both sides, and it gives us y bar over x is equal to k squared. And finally, I can get the x to one side. X is going to equal y bar divided by k squared. Okay, and this should be x star. It should be x star ever since we set the whole thing equal to 0. Okay. X star, so minus 2. All right, there we go. So this is what we call our best response function for the government. So to interpret that function a little bit, we see that the optimal level of enforcement, X, is increasing the bigger the government expects the crime level to be. That's intuitive, right? The more crime you expect there to be, the more officers you'd like on the street, optimally. But it's decreasing in the cost of those officers. K is associated with the cost of hiring officers. Remember, K to the fourth is the unit cost of law enforcement. So as the unit cost increases, that means that the optimal level of effort of law enforcement is going to be declining. Okay, both of those features of that best response function make sense. Now we're going to move on to the criminal side of things, and as a refresher, we have y to the 1/2, and it's going to be divided by 1 over 1 plus 1 over 1 plus x times y. I'm going to, instead of that, I'm going to make it times 1 plus x times y to the minus 1. Same thing. That way I won't be using the quotient rule, I'm just going to use the product rule. In this case, anyway. Okay, so we have this function. I'm going to take the derivative of this function with respect to y, because y is the choice variable here, which means then we have to form a guess of what x is. Okay? Now, I'm going to use both the product rule and the chain rule for this particular decision problem. Okay, so this derivative, this is complicated, and it's not worth me going into the details of the product rule and chain rule, so if these results, if these derivations mystify you, that's okay. Let's get to the point where we identify the derivative, and then we can all do the algebra together and simplify. And I'm not going to make you apply the product rule or the chain rule in the context of the exams going forward. But this is such a nice model that I still want to present it to you. Okay, so to take the derivative of this, notice that we have a product of y terms, right? They're on both sides, and so the product rule is that we take the derivative of the first term. So that means 1/2 times y to the minus 1/2. So that's the derivative of that first term, and we multiply it by the second term, which is just 1 plus x times y to the minus 1. But then we have to, that's minus 1, but then we have to add to that just the first term by itself, which is y to the 1/2, and we multiply that by the derivative of the second term. The derivative of the second term, we have to throw the minus 1 out in front, times 1 plus x times y. And that's going to be to the minus 2, but that second term wasn't just y by itself, it's a function of y, so then we have to take the derivative of what was inside, so we need to take the derivative of 1 plus x times y, we have to take the derivative of that with respect to y, which is going to give us x, right? And so that's applying the product rule initially, and then the chain rule to the second term. I don't want to go into the details of how to apply both of those rules. Again, because I'm not holding you responsible for it, I don't want to spend a lot of time on that. All right? So we're going to set this derivative equal to 0, and by and x is going to be a belief. Right? So this is the belief. We set that whole thing equal to 0, and that gives us this equation. We solve it for y as a function of x. Okay? Now, y here should be y star, but not writing it down. To keep from being too messy. We'll add back in the y star at the end. So this equation, there should be a y star there, but taking stars to the exponents is just kind of confusing. Okay? So we'll not do that. Now, with this expression, since we'll say this is the first term, this is the second term, since it's equal to 0, and since there's a minus sign out in front of this one right here, we're going to take that to the other side of the 0, okay? And then we remove the minus sign from it. So I'm going to do that first. Also what I'll do is all the negative exponents, I'm going to put them on the denominators of their expressions, right? So I'm going to make everything a fraction. So the left-hand side, I have 1 plus x bar over y up top. Ooh, that was a mistake. Easily rectified. That should have been a -1 somehow. That became a plus. I think it was when I was trying to add my plus term. Yeah, that should have been the expression by itself. Okay? Okay, so I'm going to drop all my exponent terms that are negative to the bottom. So the left-hand side is going to be 1 over 2 times y to the 1/2 times 1 plus x bar times y. Again, these y's are really y stars. And then the other side, the -1 carried to the right-hand side disappears. We're going to have a y to the 1/2 up top. We have an x bar up top. And then underneath, we have a 1 plus x bar times y. The whole thing, not to the -2, because we took it underneath. The whole thing is simply just 2. All right, so I believe that's correct. I am going to multiply both sides by y to the 1/2 to start with. So I have 1 over 2, the y to the 1/2 disappears from this side. And then on the other side, the y to the 1/2 times y to the 1/2 just gives us y. So I have y on this side now, x bar, and these remain unchanged. Okay. And the next thing I want to do is multiply both sides by 1 plus x bar times y. All right, so on the one side, I'm going to get 1/2. And on the other side, I'm going to still have the y, x bar, and now that squared is gone. So I just have 1 plus x bar times y. And now I want to get my common terms together. Multiply both sides by 2, multiply both sides by 1 plus x bar times y. So I'm going to have 1 plus x bar times y is equal to 2 x bar times y. All right. I subtract x bar times y from both sides. So I have 1 is equal to x bar times y, which means that y, and again, this is y star, so I'm going to bring my star back in finally. And that is going to equal 1 over x bar. Okay? So, it was really messy calculus and some messy algebra, but it's simplified down beautifully for us, right? So the optimal choice of crime level is simply equal to 1 over the expected level of enforcement effort. Notice that if the enforcement is expected to be 0, the crime level is infinite, right? Because 1 over 0 is infinity. So if there's no enforcement at all, you want to do as much crime as possible. So an infinite level of effort onto crime. Of course, in any kind of rationality world, that's not going to happen because that's going to impose hugely negative costs on society. So government would never let enforcement effort get that low. They're going to give some level of enforcement effort to combat that feature, but if they give too much, the cost of effort gets too big. Okay? And so this model will settle down and do an outcome of some intermediate levels of crime and enforcement. Okay? Okay, so we have our 2 best response functions. All right, so label this best response function. This is for the crime side. And to recap, I have y star equals 1 over x bar on the crime side, and on the government side I have x star is equal to y bar over k squared. Okay, now I know this chapter is on rationalizability, but what I'm going to do next is talk about, just because we work so hard to get such simple expressions for best response functions, what I'd like to do here is now show you how to use these best response functions to find an equilibrium, okay? So what do I mean by that? This is our next chapter anyway. This is chapter 9. We go to Nash equilibrium, so this is kind of like my bridge between chapter 8 and chapter 9. All right. Now, what if we, like players, coordinate in their beliefs? So the beliefs are correct. Suppose beliefs are correct. All right. That's a huge assumption, right? Like it could be, they could be way off. Like you could think the criminal could think government effort's going to be really low this year, so they decide to really ramp up crime. But it turns out the efforts are high, and so there's the mismatch between criminality and enforcement, and vice versa, right? But suppose that beliefs are correct, right? This is going to be the main assumption in chapter 9, which is going to give us the Nash equilibrium, right? So suppose that beliefs are correct. What does this mean? Then X bar for player 1, for player 2, her belief about what player 1 does is correct, which is equal to X star. Okay? So they're going to be correct. And we're also going to have that Y bar, the belief of player 1 about player 2, is also going to be correct. Okay? So they're both going to be correct in their beliefs. Well then, what do we have? We know that the best response function for player 2, Y star, is equal to 1 over X bar, but X bar is simply equal to X star now, right? Because they're correct in their beliefs. They chose the right, they guessed correctly. And we also see that X star is equal to Y star divided by K squared. Okay, so if beliefs are correct, we have this system of equations. We can plug these two equations into each other. Right? So we substitute, and we find that Y star is equal to 1 over Y star divided by K squared, right? So Y star is equal to K squared over Y star, which means that Y star squared is equal to K squared, and since K is positive, we know that Y star is simply equal to K. Okay? So in our equilibrium, so when we know that each player knows each other's best response functions and assume that the best response functions are being played, and so that they're going to be correct in their beliefs, we have that the optimal level of crime is simply equal to the optimal level. The one K is proportional to unit cost of police enforcement. So the unit cost of police enforcement is K to the 4th. So as that unit cost increases, so does the criminal activity. Boy, that makes a lot of sense, right? So if police officers are expensive, right, well then crime is going to go up, right? Because not as many are going to be hired in equilibrium, right? So that's a very intuitive thing, okay? And further, we know that X star is equal to Y star over K, but Y star we know now to be equal to K. And so the level of police enforcement is K over K squared, and so X star is equal to 1 over K. Okay? It's also simply a function of the parameter of the model. It's also simply a function of the parameter of the model, but now it's the opposite from the government side. So as the cost of policing increases, the level of police enforcement decreases, right? So in our Nash equilibrium, it's the first time we've actually used that expression. We see that both the optimal level of effort for criminals and for the government is simply a function of the cost of officers, right? And it's a very simple function of the cost of officers. On the crime side, it's equal to K, and on the officer side, it's equal to 1 over K. So there's going to be more crime and less enforcement as the cost gets bigger. Alternatively, you can think of it as less crime and more enforcement as the cost gets smaller. So that parameter value just exactly determines what our equilibrium level of effort on both sides is going to be. And so we can think about how the economy changes in terms of how much crime is going to be out there as a function of the cost of policing. which is a really interesting and useful result, and it's kind of the foundation of the way that economists think about crime from an economic perspective, when the incentives of all the players are taken into account in the adoption of effort levels on both the government side and the criminal side. Of course, this model can be enriched in many, many different ways. This is a very simple version of the model, but it's also a very nice one to begin to think about how the economics of crime works. Okay?